Hello everyone. I hope you guys are doing good. Today, I, Shivam, will be talking about my end-term project for advanced machine learning titled Deep Q Learning for Financial Trading. So here's a look of my dataset. We can also see that the dataset has few of the major stocks, including Apple, Microsoft, INTC, Amazon, the SPY index, as well as few of the exchange rates such as for euro. In the code, the link for the dataset has been mentioned, and we are talking about data from 2010 to 2020. For the columns, we have the closing value of each date for various stocks. And the length of the data comes out to be 2516. Here's a simple exploratory data analysis that has been generated with the help of the EDA feature of Google Colab. Next, talking about the distribution, we can see that we are talking about the stocks that are mentioned, which includes stocks like Apple, Microsoft, INTC, Amazon, GS, SPY, SPX, VIX, Euro, XAU, GDX, as well as GLD. Plotly has been used to create an interactive graph, which can help us look at the graph, point at the graph, and get the value, as well as the stock we are talking about. Next, talking about the problem statement. We know that the financial industry is characterized by dynamic and complex market conditions, necessitating intelligent decision-making to optimize trading strategies and maximize profits. Traditional approaches often fall short in adapting to rapidly changing landscape, prompting to the need for innovative solutions. The Deep Q Learning for Financial Trading project addresses this challenge by leveraging reinforcement learning techniques, specifically Q learning, to train an agent capable of making informed trading decisions. The key problems that would be addressed here include optimal parameter generation, maximized profitability, data preprocessing challenges, generalization to deep reinforcement learning, and a broader context of reinforcement learning in finance. Here we can see our deep Q learning agent, and at first I have initialized my variables. For the deep Q learning agent, I'll be using a gamma of 0.95. At first, using a hidden units of 24. These 24 hidden units are the neurons in my hidden layers that would be used as a base learner. Here I'm using the Adam optimizer, a learning rate of 0.001, and I've defined a flag finish which I have initiated to false. Here I have the epsilon of 1 and a minimum epsilon of 0.01. The epsilon decay has been put to 0.995, a batch size of 32. Max reward have been initialized to 0, and I have a list for averages as well as memory. So here is my first model, which has just 2 hidden layers with 24 hidden units, and the output layer has a loss function of MSE and a learning rate of 0.001. I've also defined the act and replay method as well as the learn method to keep updating the optimal policy after every iteration. So for the parameter generation of the optimal model, which has been talked about later in my project, the parameters that I have been using include R, S, M, V, and D, which are log returns, simple moving average, momentum, volatility, as well as direction. I've used a value of +1 for direction if the lag is positive, else I have used the value of 0. So talking a little about Q-learning, here we have a reward function. The reward function are assigns to each state action as a pair a numerical reward. We have an action policy which assigns to each state S an allowed pair a numerical value, which consists of immediate reward of taking an action A and the discounted delayed reward, given an optimal action taken in the subsequent state. Due to the approximation capabilities of neural networks, they are typically used to represent optimal action policies Q, and I'll be using deep neural network for the same. In these neural networks, features are the parameters that describe the state of environment, and labels are the values attached to each allowed action. I would also like to talk about my improved finance environment. Similar initialization has been done here. We have a symbol which gives us the symbol of the stock we are talking about. We have the features that are to be used as the observation space. We have the window. We give the value of window, and I have used a window size of approximately 25. We have defined lags, leverage, minimum performance, start and end, mean of the data mu, and standard deviation STD. So talking about the exploration versus exploitation trade-off, the exploration refers to actions taken by agent that are random in nature. The purpose is to explore random actions and their associated values beyond what current optimal policy would dictate. And exploitation refers to action taken in accordance with the current optimal policy. We also defined replay, that is the continuous updation of optimal policy given the new experience, which we'll be learning using neural networks. We have defined epsilon, which as shown in the code I have used as 1, which is the ratio with which the algorithm relies on exploration as compared to exploitation. When we start learning our model, we have a complete focus on exploration and exploring new criterias. As long as we start and dive deep into our model, we stop exploring and start exploiting what we already know. For that, we use an epsilon decay that is defined as the rate at which epsilon is reduced. Here we are talking about the initialization of parameters, and this is for the updated financial Q-learning agent. Here we can see that I have used an epsilon of 1, a minimum epsilon of 0.1, an epsilon decay of 0.98, a learning rate of 0.0001, a gamma of 0.95, a batch size of 128, and initiated the max reward as 0. And I have few lists that I have used to store the maximum rewards, the averages, the performances, the A performances, and the V performances or the volatility performances. For the memory, I have used DQ with a maximum length of 2000. Now talking about the training, at first I have trained my model for the stock AAPL, or generally known as Apple. For the training, I have used R, S, M, and V, the log return, the simple moving average, the momentum, as well as the volatility. A and B defines the starting and the ending position of our training data, and from B to C defines the validation or the test data for our model. For the learning environment, I have passed on symbol, features, a window equals to 10, a lag equal to 6, a leverage of 1, a minimum performance of 0.85. That means that when we'll have a loss more than 15%, we'll stop learning that. We can see the start as A, the end has been set to A plus B. That's the end of our training data. We have a mean of none and standard deviation of none that would be later calculated as defined in the FQL agent. Now, talking about the validation environment, we have the same symbol, features, window, lags, leverage, minimum performance, start, A plus B, and an end value of A plus B plus C. In our case, it goes on from 2000 to 2500. Now, for the validation, we would have a mean value of learn env.mu and a standard deviation of learn env.std. So here, after setting the seed and calling out our FQL agent for hidden units equal to 48, a learning rate that I have been talking about of 0.0001, a learning environment and a validation environment, and a flag equals to true, we continue our training for 150 episodes. We can see the following training. Our training starts and goes on till 150 episodes. And we can see that our rewards increase from 83 to 494, and our performance increases from 0.838 to 1.895. And our epsilon is continuously deteriorating from 0.68 to 0.1. It goes on till 0.1 because we have set its minimum value to be 0.1 so that it cannot go beyond a 10% exploration rate. Here, a performance of 1.895 entails that we can have approximately 189.5% returns on our Apple stock. We can also see that the maximum performance was achieved at episode 107, where we were able to get a return of 1099% or a 10-fold return. Now, talking about the graph generated using our model, we can see that for the training, we were able to get few mind-blowing results that were more than 10 folds. Similar were for regression, that was around 5.5 at maximum. For the validation purpose, we see that our minimums here are at 85%. These minimums are used to stop training whenever we go anywhere lower than 15% of loss. And we can see that after approximately 130 episodes, we have achieved a stagnant validation graph. This helps us understand that using these parameters or the trained models, we can go ahead and obtain a return approximately 200% for the Apple stock. So moving on further, I was also trying the same for the USD Euro trade-off. And moving ahead with the similar parameters, I was able to get a result which was quite mediocre. This was because here my model was suffering the issue of being overtrained, because we can see we have at times very high accuracy for our training data, but for validation, it's been the same, and it's given us a return of approximately 8.9% throughout. I would like to thank my professor for giving such important lectures on LSTM, which has helped me to maintain a basic understanding of time series and help me move ahead using reinforcement learning for my term project. And that's an end from my side. Thank you.